So we're not focusing on statistics in this class, but we need to be aware of statistics and use them as appropriate. But still want to make sure we're all coming at our philosophical graphing approach with a statistical frame of reference. That's what I just want to talk about now. It's if you guys haven't been thinking about stats for a while or whatever, just kind of begin to reposition us in terms of thinking about this. So statistics might sound boring and lame to us, but the reason we use them so much in the sciences and elsewhere is because it helps us understand the world, right? It helps us predict what's going to happen. And so that could be something like, is it raining today? Or that could be something like, is this coin an evenly balanced coin? Or is it a loaded die or something like that? And so, there's all kinds of examples we could give, but here's but one from a long time ago from someone who's now passed away from CNN. And so this guy says, my next guest tonight is making some remarkable assertions about the causes of our recent violent weather. He says we face the man-made threat of terrorist hurricanes. He says Katrina, meaning Hurricane Katrina, for example, was created by the Japanese mafia using Russian-made technology. What the F, right? I mean, why is that person even allowed on television, right? It's all not true, and a simple look and a simple basic understanding of probability would tell us that there's no way the Japanese mafia is terrorizing us with hurricanes, right, or whatever. But because many folks don't have statistical training or don't have a general grounding in some of these critical reasoning things, that allows people like this to, get on CNN or Instagram and TikTok and stuff now. Okay, so we're talking about a couple basic things here. So one is statistics and one is probability. They're basically the same thing. They're just a different direction on the arrow. Statistics is we sampled something. So we're trying to understand the world of the marbles, right? So the marbles are in my bag. And I want to know, what's the deal with the marbles? Are there striped marbles? Are there black marbles? Are there white marbles? Are there spotted marbles? I just want to know how many marbles there are in my forest or in my area, right? And so what I do is I go in and I don't count usually I don't count every single marble, because usually the bag is too big for us to do. It's the whole ocean, it's the whole county, it's the whole whatever. So we go in and we grab a couple representative things, in this case marbles, from the big group of things, and I call that my sample. And so what I'm trying to do with statistics is from a sample predict what is in the bag. That's statistics. Probability is the reverse. So probability is I know all the marbles that are in my bag. Okay, I know how many striped, how many this, how many that. And then I'm going to reach in and grab one, let's say, grab one out. What color is it going to be, right? That's probability. So it's the same basic idea. It's just sort of one is going forward and one is going backwards, but it's the same thinking. Cool? Everybody with me on that one? Okay. And so basically, let's look at the simplest of the simplest thing, which is a coin flip. It's just A or B, right? And so, so the question is, hey, is this quarter I'm going to flip? Is this just a regular old quarter, which it's evenly balanced? Or is it something somebody did something to and made it heavier, so it's going to come up heads more frequently or whatever, and then we're going to go bet on it and they're going to make a bunch of money off me, or something like that. So is it really just as likely to come up tails and just as likely to come up heads, or is there some bias in there? So we want to say, hey, how do we know if something's up? So we're going to sample this, and so we're going to develop hypotheses, and this is the same kind of thing we're going to do with our figures, right? We're going to do this conceptually. So the basic idea is our null hypothesis is that there's no difference, in heads and tails. It's like just as likely to come up heads this time when I flip it as just as likely to come up tails if I flipped it, right? So that's our null hypothesis. The null hypothesis is usually no difference. Or no effect of the thing we're measuring, okay? The alternative is that there is some difference. That's all it says. There's some difference. It doesn't say if it's higher, it doesn't say if it's lower, it doesn't say if it's heads, or it just says there is a difference. And so the general approach, remember, for our statistical thinking and how we should approach when we're building arguments with our figures and all that kind of stuff is we will default to assume that the null hypothesis is correct. There is no difference. There's no effect of my variable, let's say, until we get enough evidence that it actually is, until we get enough evidence that the heads are really coming up more frequently than just, 1 out of every 2 times on average. So that's how we approach. And so until we have evidence, we keep assuming there's no effect, there's no difference, there's no change. And so here we talked about a coin, but it's the same exact thing of saying, hey, does the fish exposed to the pollution stream get sick? Does the grassland that was burned more frequently, does it have more birds in it? It's the same basic idea, right? We're just asking, does A differ from B? And don't get confused if the A is really pretty or fancy. It's just an A and a B. And so essentially what we're talking about now with the coin flipping, with the fields of grass, is I have a population. I have this table, and I want to compare it to this table. Okay? And so now I need to describe this table's population, describe that table's population, and then see if they're different. Does being at table A matter, or does table not matter, right? With whatever the thing we're talking about, height, loudness of the voice, whatever the variable is. And so here is a version of that figure I told you last time that I got in super trouble for. So this is the one that my postdoc advisor was like, "You dumbass, why did you? What?" But so this is it, right? So he couldn't see the difference between the green and the pink when I made it. So I thought I'd show you guys my lame figure, right? How horrible it was. Okay, so let me explain to you what's going on, and then let's talk about how we sort of bring how that thinking might influence how we make a figure. Cool? Okay, so let me just, again, every time we put it up, let's orient our viewers to it. So let's make sure we're all on the same page. So I'm looking at the success of a restoration. Okay, so we had a degraded ecosystem. I did something to it, and I want to get it healthier. Okay, so on the x-axis here, this is time since I started. So we can also call that the age of the restoration. So I did something here, okay? Doesn't matter if it's hours or weeks or months or years, it's time, right? So it goes from low on the left to high on the right, okay? And then on the y-axis, same thing. It's gonna go from low at the bottom to a high number on the top. Again, doesn't matter what the numbers are at this point, it's just conceptual. In this case, the y-axis is function, ecological function. And you pick your favorite thing. You pick biodiversity, you pick height of the plants, it doesn't matter, right? But it's some measure of the ecosystem, what it's doing. Cool? Everybody with me? So I'm showing you 3 possible pathways here. One pathway is what we might call a failed restoration. So I did some stuff, but it's still crappy. There are no plants there are no birds there, whatever it is, right? The biodiversity is low or whatever. So that's the bottom one. If you guys are colorblind, this is the one on the bottom. Okay, so this is the failed restoration. Up here, the green one, the line at the very top, that's a reference site. So that's a site that we didn't screw up in the first place. So that's the nice forest, that's the nice wetland, that's the nice whatever. Okay. And so just looking at it, it looks like there's a difference between the pink and the green. Everybody with me on that? Like even just at the starting point, the red or the pink is this level, and the green is a much higher value. And what I would like to see, because I'm such a great restoration ecologist, so of course I would never fail. I fail all the time, but of course I don't want to tell you guys that. So I'm going to start off, I'm going to do my intervention, I'm going to do my activity, do my planting of plants or whatever I'm doing. And then over time, I'm hoping that the biodiversity, let's say, the species richness, goes up and basically becomes like the reference site, becomes like my ideal, my target, my destination. Does that make sense? Cool. So a lot of times when I say, hey, you guys, go go make me a graph of restoration success. This is what a lot of people will do, or something like this, right? So like, hey, okay, so yeah, I measured it here, and it came out like this, but that doesn't, I mean, that's a starter. Okay, good, first thing, but that's not enough. What I really need is I need to see something more like this. I need to see both my average value, but there's noise, just like we were talking before about stochasticity, there's noise in everything. Ecological systems are noisy. So I'll tell you the story of one of the reasons that I get super annoyed at physicists. I have things with physicists. But one time I was doing this study with some plants, and we had this big fancy machine that measured photosynthesis, and we had this special chamber, and it clamped down. Now you can get these for relatively cheap, like a few $1,000s. But back then, it was a brand new machine. It was like tens and tens of thousands of dollars for this big fancy thing. It took like tanks and people to carry this out the wetland. So we carried this thing out the wetland, and we clamped this machine down on the leaf of this plant. And we shot photons into it. We shot light into it. And the plant photosynthesized and breathed out all this oxygen. And the chamber would measure the oxygen. So we generate what we call a PI curve, a photosynthesis on the X, and irradiance on the X and photosynthesis on the Y. So like, how healthy is a plant? If we gave it a lot of light, does it make a lot of oxygen? That kind of thing. So we started doing this, and the machine would plot out, kind of like this yellow line, would plot out the curve, the accumulation curve. So we start off, and there's a little bit of light, and it makes a little bit of oxygen. Then we give it more light, and it makes more oxygen. And so we start doing it, and instead of being a smooth line, it would sometimes get really jerky, like really like a heart attack, like up and down. And he'd go like, this is wrong. Like, what? Like, must redo it. I'm like, what? Like, got to redo it. I'm like, oh, okay. Like, I didn't know. Like, I guess he didn't do the seal correctly or something, right? So do it again. And same thing. It comes up, and it's noisy. It's a noisy line. And he goes, got to redo it. I was like, oh, what do you mean got to redo it? Goes, yeah, got to redo it. I was like, I thought you said you got the seal right. He's like, yeah. Like, well, but it was jerky. I was like, okay. And he was like, so it can't be right. So he was coming from the world of physics, which is very powerful and all kinds of cool stuff, but it's very, traditional physics is very deterministic, right? It's force equals mass times speed and all those things. And so in his mind, that couldn't possibly be right, because all the other times he did it, it was a nice smooth line. So noise indicated something was wrong. I was coming from the biological world where the whole world is nothing but noise. It's like sometimes that bug is really long and sometimes that bug is really short. And that's just sort of the ecosystem of the beauty of the diversity of this world that we have. There's not all the trees are the same height, right? But he was like, no, dude, we gotta delete it all until it's all like perfectly pretty. And we had issues. Anyway, okay, so but this, when we're doing stuff, most of the stuff that we're dealing with, there is noise. Some people rebuild, some people don't. Sometimes the sea level gets really high, sometimes it's just kind of high, right? All that kind of stuff. So when we make our visualization, we always want to include the variation, the spread, right? Everybody with me? So we could imagine a case where what if this pink line, or excuse me, what if this yellow, so right now, it looks like the main signal and the noise of the green is really different from the pink, right? The noise, they don't overlap. So it seems like we could clearly segregate greenness, or the top line, from pinkness, or the bottom line. But let's imagine instead that noise was, as wide as the top of the screen. In which case, even though the lines look like they're different, they're so noisy, maybe we would not be able to distinguish a green from a pink. Everybody with me? So understanding both the middle part, both the central tendency and how noisy and how messy it is, that's what gives us confidence that there really is something different, okay? So you might be more familiar with this like this. You might be more familiar seeing this in your intro textbooks. Okay, so here is a measure of something. It doesn't matter. Let's say height. Let's measure everybody in Sierra Hall's height, let's say, okay? And so this x-axis maybe would be how tall we are, let's say, maybe. And then on the y-axis, that would be how many people are that tall, right? And so we'd call this a normal distribution or a normal curve. So we have a few people that are going to be tall, really tall. We'll have a few people that are really short, but most of us are in the middle, right? So that's most of our populations. Not all, but that's most of the things we deal with in most of the time. So we'll start with that as our default thinking, as we're thinking about making graphs and things. And so the two key things I want to point out here are, one, the central tendency, right? Which we normally think of as the average, but there's other ways to measure it, but average is a fine way to say that. And then how fat is this? How wide is this? How noisy is this? Is it a little teeny tiny perfect spike where almost everybody is that height? Or is it very slow and spread out where very, very few people are actually that height? Everybody with me? And why that matters is because what we want to do is we want to say, hey, do the heights of people in Sierra Hall differ from the heights of people in Bell Tower? And so we're going to, yeah, okay, great. Oh, I guess I didn't show that. Okay, this is what I want to show. So this is what we want to do, right? We want to say, hey, because things will always be different. No two things are rarely, if ever, are they exactly the same. So, okay, so one building has people this tall. The other building has people this tall. And the question becomes, is that really different? There'll always be some kind of difference, but does that matter? Does that difference matter? Was it just because of the random folks that we measured? Or is there really something about people that take classes in Sierra Hall that on average they have a different height than people that take classes in Bell Tower, right? And so statistics gives us the power to understand that, to see, is there really a difference, or is it kind of looks different, but it doesn't really mean anything in the real world, right? And so that's all we're doing. And so for example, in this case, I was saying, let's talk about the size of fish. So we have one, Professor Spies would love it if it's here because it's fish. And he'd be like, I love fish, I love to fish. And then I like to fish, right? So we'd say, we got kelp bass, and he'd be all excited. He'd call him calico because he talks that way. And then these are sand bass. And so, okay, so we have like this dude is, so this population, this group of, we caught a bunch of fish, and we measured all the fish. And then I found out that their average length is 181.6 millimeters, and the sand bass are 241. So at first look at it, you're like, oh, it looks different. It looks different, right? Because it's like the numbers aren't the same. And then we have a standard deviation, and we have about the same number of samples. They're a little bit different, but we have about the same number of samples. And so this mean length is the central tendency, is the middle of the hump. And the standard deviation is a measure of how broad it's spread out. And so again, the null hypothesis, we always start, there's no difference. Bell Tower and Sierra Hall, no difference in height. Fish species A, fish species B, no difference, right? So that's our null hypothesis. And then if we find evidence to reject that, we accept the alternative, which only says it's different. It doesn't say one dude's bigger than the other. It just says someone is different from someone else, or some population is different from another population. This is making sense, you guys? It's all good? Okay. Okay, so then if we actually go down and we can calculate it and we get these numbers, this is actually how we do it. We're not going to do that by hand, but you could do it if you wanted to. So to do this, what we can refer to this as is as a t-test, which is a simple compare population 1 to population 2. Are they indistinguishable from one another, or are they different? And in the simplest case, with just one group and just another group, we call that a t-test. And because it doesn't matter, YT, why not X? Because I didn't invent it, and the dude that invented it was like T. And so we call the statistics T, right? That's it. There's no other reason. And so, but back in the day, like now you guys are like click, 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 boom, right? Pull down my data analysis pack and boop. But back in the day, we had to do this all by hand. And so, so we developed a lot of sort of shorthand to help us with this. And so I'll just say that back in the day, you had to do it by hand, and we don't care about that. But well, okay, right. But just conceptually, the top thing is the signal, is the mean, is the main boop, the main signal, is this thing, is this part. So that part is the mean. This is the average value for any one point in time. And then the variance is this noise, is this cloud surrounding it, the error. And so we're basically essentially taking the signal to noise ratio, right, conceptually. So if we have a lot of noise, it's hard to see the signal, right? Unless the signal's really, really big. If the differences are really subtle, we want to make sure it's very quiet, right? We want to have a lot of samples, which will help us reduce the noise so we can be much more precise and pick out the very fine differences in signal. So it's always easier to see a difference when there's a large magnitude difference, and as the difference gets smaller and smaller, it gets harder and harder. It gets harder on us because we have to take more samples. It gets harder statistically because we have more assumptions and things, but conceptually that's what we're trying to do, okay? And so we come through, we get a number, and then back in the day, you would have to go look this number up in a table. So all my old statistics texts have all these tables in the back. And so I'd go and I'd look up 7.41 and I'd go, blah, 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 do my thing. And then I'd figure out if it's good or not. But the main thing we just want to make sure is that, because there's always a difference, and what we're using statistics to say is that this difference is very unlikely to happen just randomly, just due to chance, right? There's always a possibility of chance, right? There's always the possibility that, I don't know, somebody funny, Dojo Cat makes a hit single or something, right? There's always a possibility that'll happen, right? But we want to know that on average, is that likely to happen, right? And so we're using, right, so we're asking is it big enough? Okay, so essentially what we're doing is we're using this degrees of freedom, and we're basically saying, hey, is this different? You can use Excel to do this, or any of our other statistics programs, right? But in effect, we're saying, do these curves overlie each other? And so this is where the p-value comes into play, right? If you guys all remember the p-value, p stands for, p actually does mean something, unlike T and R and these other things. So P stands for probability. So that means the probability that we would have gotten this difference of these two populations just randomly due to chance. So the probability that this was just, a throw of the dice. And so purely by convention, and so in this case, the numbers that I gave you before, this comes out as 0.000000000086. Which means the probability, and so the probability, so if it was 1%, it would be 0.01, right? So it's way less than 1%. And by convention, what p-value do we usually use as significant? 0.05. Why? Because. Oh, that's the only reason. It could have been what? 4%. It could have been 10%. It could have been 1%. But some old dudes that were gamblers and like alcoholics back in Europe back in the day, they're like, F it, let's do 5%, right? And that was really it. There's no magic to why is it 5% and not 6? 5% are happening due to chance 5% of the time is equivalent to 1 time out of 20. And when they were sitting around drinking, they're like, I don't know, 1 in 10. I don't know if that sounds good. 1 in 2, that doesn't sound good. And 1 in 100, well, maybe that's a little much, right? So they got to essentially 1 in 20. And there's nothing other magic than that. And so we say that is a by convention thing. These other things are like mathematically proven and this and that. But why are we using this particular cutoff? It's because we needed something, right? And so this is the term we use for statistically significant. P equals 0.05 or less is statistically significant. And we say that if it's got a chance of happening that way purely because of random chance, if that happens 5% of the time or less, we're pretty confident that these populations really are different. That the pink line really is different from the green line. Does that make sense? So as we're crafting our visualizations, we want to make sure that we're thinking of this, right? That maybe not the very first thing we put on, but as we start to get a little more sophisticated, we want to always have that noise incorporated into how we're presenting stuff, right? Because we don't want to mislead people, we don't want to mislead ourselves. Okay. Yeah, and there's it pull down. Okay, and there's stuff about two tails. Forget that stuff. Okay, so this is in principle. This is how you guys are going to approach your visualizations when you want to see if something really is different or not. we're going to start off. We're going to generate we're going to look at our data set and check it all out. And the first thing is we're going to look at the summary stats. So before we do anything, before we graph it, before we do it, and that's essentially just let me put my arms around it. What's the biggest number? What's the smallest number? What's our sample size? How many individuals are, how many lines or whatever are in there? Okay, cool. Then, after we've gotten that, the next thing is let's take a look at the central tendency. Let's take a look at the middle of that peak. What's the average value of my population A, my population B? Okay, that one's about 100. That one's about 90. Okay, cool. And then we want to sort of get a sense of the variation, right? So is it all over the place, or is the variation pretty tightly hugging that central tendency? Okay, and then once we kind of have that sort of in our brain, then we can start to move on to visualizing stuff. Then let's start worrying about making a graph, and let's start seeing how things lie down, right? And so one of the things we also have noted over the years that has been a declining skill is guesstimating. Estimating roughly. So where I saw it was with my son, who always sat in the back of the car, and then when he started driving, right, he's like, oh, I think I gotta go meet this guy in LA. Oh, LA, how far is LA? What? How far is LA? What do you mean? Like, how long is it going to take you to drive to LA? I don't know. No, don't look at your phone. Just tell me. And then right, because he was so used to not just being driven everywhere, he wasn't paying attention. And so same for us. So we want to be able to ballpark it. We want to be able to know roughly that population 1 is about twice as big as population 2, because that might influence what kind of graph we pick, right? One that's like really big, or maybe one that we need to emphasize, the differences and that kind of stuff. So we want to kind of eyeball it first. So only once we've checked out the data, got everything all lined up, summary stats and everything, then we're going to get to the visualizing stuff. And then once we visualize it, we're first going to make a quick and dirty, just boom, boom, right? So remember we talked about sketching something out as we get it. And then once we've just kind of gone through that, you're going to make your first one. Don't worry about making it pretty and everything. We just want to see, hey, how does it lay out? Okay, it's laying out sort of like, okay, right? And then we can start to begin to get a sense of, okay, so it looks like this thing is bigger than that. And then this one is about half the magnitude of that, and we can start to then kind of wrap our head around it and begin to interpret the patterns as to what's going on. After all that's done, then we would get to the statistics, right? So I'm not saying, we're not going through the statistics stuff because I want you to start there, but I want to have, you guys always have that in the back of your mind, that we want to be able to quantitatively communicate if something is different than not, but that's sort of, step 6 in this process. Cool? General questions about that? Does that make sense?
So step 6, you're still talking about the data or about the...
Mm-hmm.
Okay.
Yeah. So the problem is everything is so nice and contained for you guys with all these pull-down menus. It's very, very easy to, Dr. A gives me the data, scatter plot, barf, right? And no, that's not the right way to do it, right? Let's first take a look at this. Like, okay, what are my values? Okay, are they all over the place? Are they all pretty similar? Is one bigger than the other? Okay. And then let's see what the middle point is. Let's see what the noise is. And then I want to start to do my first figure, right? And just like everything else we talked about, it's the first figure. It could be totally wrong, right? And you're like, ooh, God, that's probably not the best way. I should probably use a bar chart here, or I should probably use whatever, right? And we're kind of going to go back and forth. And then once we kind of get the sort of rough idea, then we'll start worrying about making it pretty. Then we'll start worrying about making, overlaying all the data. But it's just so easy for you to start barf, 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 barf. And we don't want that. We want you guys to be thinking purposefully when we get there. Still explore, still have fun, but just don't immediately jump to the graphing button. Sorry, if they're all were what?
All words.
If the statistics. Sorry, I don't understand.
If you, for an example, the data set we have, if it's naming different locations.
Oh, non-numerical. Oh, I see what you mean. Okay. All right, good. Excellent question. So William's question is, what if it's not, so we have 3 this is for another lecture, but we basically have three broad categories of types of data that we use. One is called a continuous variable. Continuous variable is like this, right? So it could be anywhere on this spectrum. It could be 1, it could be 3.9, it could be 7.4, right? So that's like numbers, right? Typical temperature, right? Something like that. Okay. The other kind, so on the other extreme, we have what are called categorical. Eye color, blue, hazel, brown. So those are clearly distinct, and we can tell that blue is different from brown, but it's not like that brown is twice as much as blue or anything like that, right? So they're in bins, but it's not as if one bin is above another or below another. They're just bins. Again, we call that categorical. And then we have stuff that's kind of in between. So they're in bins, but the bins have some quantification associated with them. So what do I mean by that? So I mean, we get a lot from when we do survey data. So how often do you eat seafood? Never. Sometimes weekly. Okay. So those are bins, right? Those are categories. But one is 0. One is never eat the seafood, right? One is eat a lot of seafood, and one is eat a little bit. So the little bit is definitely bigger than none, but it's not as big as a lot. But I don't know. But does that mean it's like 1 unit more than none, or it's 10 times? Is it half as much? We don't know. So that one is we call it semi-quantitative, right? So and each of those have different types of approach, different types of tools we can use. So the short answer, William, is that we would do some type of coding on that. So if we had people that said green box, we would code them as the green boxes. And if somebody were red round containers, we'd code them as red round containers, etc. And so some of that is very easy to do. In other cases, you might have to make a judgment. So maybe some people have said they were green boxes, and other people just said green or boxes.
Well, how would you...
So you could do a bar chart, for example, and a bar chart could be North America, South America, whatever.
I understand.
So yeah, so we're out of time, but how we can do that? And let's only just finish this real quick, and then I'll answer your question. So here's just some examples of how we can look at distribution, but we're out of time, so we'll just say that, blah blah blah. And I'll just finish to say that there's that basic idea of a t-test, compare a population of B. Now we can do A to B to C to D to E, same exact intellectual thing. It's just we need a little more math, and we call that an analysis of variance as opposed to a t-test. So if I did an analysis of variance of population 1 versus population 2, that is identical to doing a t-test between those guys. T-test, you can only do 2 things. And ANOVA, you can do many, many things. Okay, so I just want to finish that, and then I'll answer William's question. So I'll just say blah, blah, blah. Yeah, well, we can talk about this later. So just real quick, statistics and probability, same thing. It's just one's forward, one's back, but it's the same intellectual idea. The key thing here is we're testing hypotheses. So, and that's what we're trying to do visually with our graphics. We're trying to, hey, is this thing different than that thing, right? And we talked about the basic description of just about all of our populations we're going to want to look at, whether it's written with words or written with numbers, is summary stats, basic qualitative deal, and then measure of central tendency, measure of dispersion. And then the most common things, if we're going to compare 2 things, the most common tools we have are a t-test and an analysis of variance. And it gets much more complicated after that, but that's the basic idea. Does that make sense? Is that ringing historical bells with your stats class and stuff? Okay. All right. Okay, so that's all I have for you tonight. But let me, so we'll get to this stuff.